All right, let's get started here. This is going to be worksheet 11, the special theory of relativity. This is going to be going over some of our key concepts, and a few of these questions here are kind of what you have seen on the homework. So that should help you guys in working on that. So I'm here, by the way, a little off frame right now. I'm just going to go through the equations. These ones are kind of lengthy, so I typed them out for us just so we have everything organized. Also, I think that it's easier for me to explain when I'm looking at it and you guys are looking at it. So please look at the key formulas table that I provided here. And then there's actually a few more equations I'm going to want to add to this list. But I will write those ones on the board and we can talk about them. So I guess the first thing I want to do is kind of establish our framework for solving these questions. So I think that we can all recognize like relativistic speed and whatnot, but the most important part, or at least to me, the most important part is being able to recognize what is our stationary frame. So that's like what like the observer on Earth would be, and then what's our moving frame, right? So the key difference here is that like a stationary frame will always observe a normal distance traveled, right? But the actual event will take longer. So if you think about it, the like v equals d over t, so that's velocity equals distance over time. We go back to 135a and think about that equation. For our stationary frame, they really see the time as the relative event, if you will, right? And the length they see is the normal length. So it's like actually what it is. And then conversely, when we're thinking about the moving frame, we need to recognize that they're actually seeing a length contraction. So that means like the distance traveled is what's relative, right? So when we think about that v equals d over t equation, that distance is what's relative. So between the two, the stationary frame has time, which is relative, and the moving frame has the distance, which is relative. So then I want to now look at our time dilation and length contraction equation. So that's going to be equation number 1 and number 3 here. Just by definition of time dilation, you know, where delta t is the observer time and delta t naught is the proper time. So proper time could be like, I have a particle that has this half-life. I have an organism that lives this long. So the proper time is like how it is, like if you think about it on Earth, like quotes on Earth. And the observer time is what is like what's going to be expanded, right? So when you think about this equation, you will always be able to say that delta t is going to be greater than delta t naught, right? So remember that delta t will be greater than delta t naught. And that can kind of guide us selecting what frame is what and what's going to go where in our equation. And then alternatively, if we look at length contraction, we'll see that you know, L equals L naught, where you know L naught is the normal length, and L is like the observer outside of the frame of reference. So that's like what's on the moving thing. So L then will be smaller than L naught. So let me repeat, delta T is greater than delta T naught, but L is smaller than L naught, right? And that's because L is going to have a length contraction. So to the moving frame, the distance traveled is shortened, and to the stationary frame, the time, like the event like happens slower, okay? So that's kind of our key differences between time dilation and length contraction. And it's important to recognize like what goes where in those equations. So that's why I kind of gave us those quantitative indications to think about something one way or another. This part 2 here, equation 2, is the Lorentz transformation. So here, the Lorentz transformation is basically a relationship between two different coordinate frames that move with a constant velocity relative to each other. So basically, it's going to be like, I remember there's like a question in the homework where two things are moving in an axis to each other. Excuse me for 1 second. All right, sorry about that. So yeah, where was I? So the Lorentz transformation, so it's, you know, the relationship between two coordinate frames that are moving with a constant velocity and relative to each other. We saw that on the homework, right? And, you know, it's like two things, you know, and they're like moving together, right? And they tend to, in our class, kind of like isolate it to one dimension. So like they'll both be moving along the x-axis, and that kind of makes solving easier. And I think that's what they actually did in the homework question too. So you kind of have a tip off on that. So now we've talked about those three equations. Next is total energy. So total energy is an equation that we're going to have to reference a lot, especially like, when we're solving for kinetic energy at relativistic speeds and or like finding momentum, right? Which is a good segue into relative momentum, which is the next equation listed here. And actually, for that matter, this was one of the homework questions, and we're given total energy, and we need to work backwards and find momentum. So you can see, like I did like a little rearranging of equation there. But I mean, I shouldn't get you guys confused, because this is actually total energy based on momentum. And this is kind of a different expression. But I guess, yeah, that's like a good thing to keep in mind. That'd be this expression, right? So that's total energy based on momentum. The only other ones I want to bring up here now, let's see. Wrote them down. I guess relativistic velocity addition. So that equation is, this is like the Klingon example. I think like someone's getting chased. I don't know, something about Star Trek in the homework. And that equation basically has, so we're gonna have like U prime equals U plus V divided by 1 plus U times V divided by C squared. So this is relativistic velocity addition. So it's basically like you have an object relative to another one, and you need to make one of them like basically serve as the quote stationary object, and then you can compare them through this expression, right? And the only other one I want to bring up is the kinetic energy at relativistic speeds. So the kinetic energy itself, this is where kind of this equation is a little bit spicy, and we will reference this again later. So yeah, remember relativistic addition, velocity addition, just erase that. And then kinetic energy at relativistic speeds is KE equals, so I'm just gonna say energy, all right, total. And then it's going to be minus the rest mass energy, or mc squared. So mass of the object. And then remember, we have alternate expressions for E total, right? So that can be the one that recognizes momentum, or the one without momentum and rather has a velocity in there. So kind of dealer's choice, pick what fits. We're going to go over the scenarios to use them. So yeah, E total, that's that equation 4 where there's a kind of 2 avenues you can go with as demonstrated in the formula sheet. All right, so we definitely had to establish some footing for these questions. I'm glad that we did that. And now we can go ahead and get started with the problems. All right. Sorry, I have to erase a little bit. I must say that somebody on Thursday evenings uses this room to like study organic chemistry with their friend. They come in, they like have their kava dinner, it smells, they leave their kava bowl in the trash, the whole board's covered in stuff, they break all the chalk. Not complaining, but if you know the kava eaters, let them know. It stinks in here Friday morning. Anyway, so here we have particle X. It's an elementary particle. Sorry, I'm making sure I'm actually recording. I've actually done a whole session where I thought I was recording and I didn't record. And another time I did a whole session where I was recording and muted. So yeah, that's fun to do the same thing twice back to back. So here we have particle X, elementary particle. They give us its lifetime when it's at rest. So now we have a proper time, right? So we already know what our stationary frame is. And how fast does X move when X has a lifetime of 5.5 times 10 to the 8 seconds? So if they already telling us it at rest wasn't enough, knowing it's a stationary frame, the fact that 2.6 times 10 to the minus 8 is smaller than delta then 5.5 times 10 to the minus 8 lets us assign our delta t and delta t naught, right? So where delta t naught equals that 2.6 times 10 to the negative 8, again, smaller than the delta t, which is 5.5 times 10 to the minus 8 seconds. We now need to solve for v, where v is going to be expressed through a time dilation expression. So we know our time dilation expression equals, I'm going to start over here. So this is number 1. So delta t equals delta t naught divided by 1 minus, I'm going to say v over c squared. We can square root that whole expression. We're going to, oh, shoot. I was like, what the heck? I don't remember that. Bottom part is what's square rooted. And we're now going to multiply both sides by this denominator to get the delta t's on the same side. So I'm going to say square root of 1 minus v over c squared equals delta t naught over delta t. We're going to want to solve for that v, so we're going to square both sides. We're then going to bring. Then we're going to bring. I'm just going to write it. 1 minus v over c squared equals delta t over delta t naught over delta t squared. So then we're going to bring this to the left side and bring this to the right side. So 1 minus delta t naught over delta t squared equals v over c squared. We now square root both sides, multiply by c, and we'll find that v equals c square root 1 minus delta t naught over delta t, and then we can square that, and then v equals 0.88c. Okay, so pretty simple example, but it's to kind of get us thinking what goes where. Let's move on to number 2. All right, so number 2, this is going to be another time dilation question. So we have Bob moving with respect to Alice with a speed v. They're both inertial. Wait, am I reading the wrong question? This is Lorentz transformation. Okay, so time dilation is a part of this, but we're going to also use Lorentz transformation. Okay, so Bob moves with respect to Alice with speed v. Both Alice and Bob are inertial observers. Their x-axes are aligned. Bob's velocity is along the x-axis. When Bob measures a time interval of 30 seconds on his watch, Alice measures a time interval of 45 seconds. This is a 3-part question. We're going to start by determining v. So to solve for v, that's going to be time dilation. And then we're going to need to use Lorentz transformation in parts b and c, right? Yeah, because we're going to have to find the differences between them. Okay, so let's not get ahead of ourselves. Let's just work with part A. So right off the bat, how do we define our delta t naught versus delta t? We know that delta t is going to be the one that's bigger. It's going to be the one that has that time dilated in our stationary frame. Delta t is going to be 45 seconds. And well, I just realized on the video, you guys can't even see my face, and all you see is the tiger shirt. It's kind of cool, huh? And delta t naught is 30 seconds. Again, our expression is the exact same. So we're going to say delta t equals 45, or actually, I already kind of discussed that. We know what they are. We're going to say delta t equals delta t naught divided by 1 minus v over c, this guy's squared, and square root the bottom. And also you guys will see it's technically, v squared over c squared, but sometimes I just do that whole expression squared. And that goes for a lot of the equations, especially like the energy total, just because I don't like to individually square every expression, because as it is, these equations can be complicated enough due to the really small or very large nature of these numbers. So sometimes I'll just like pop square out, but principles apply. At this point, we can see that it's going to be, we're going to plug in our 45 here, and we're going to plug in our 30 here. 1 minus v over c squared. And then we're going to say, we're going to get 30 over 45. We're going to do some rearranging. So 30 over 45, which actually equals 2 over 3 for that matter. And that equals the square root of 1 minus v over c squared. We're now going to square both sides and get 4 over 9 equals 1 minus v over c. This guy is still squared. At this point, I'll let you guys drive the rest of this to solve for v, and v comes out to be equal to v equals 0.745c. All right. So now that we have our v, we can start thinking Lorentz transformation. And if we recall, the Lorentz transformation is the relationship between two different coordinate frames that move with constant velocity and are relative to each other. So what I first want to do here is, I'll just read the question actually. So Alice sees two flashes and they occur at x1 and t1, and then at x2 and then t2. According to Bob, we're going to want to find the delta x, right? Delta x prime, excuse me. So the first thing to do is, we're going to write the equation to find the x primes, and then we're going to have to find the difference between these x primes. So I'm going to write part B here. I need a drink of water. Water. Take a drink of my coffee then. All right. So we already know the normal x values, but we need to find the prime values. So that's through that equation that I think we have on the first page there. So we'll see that we'll say x prime equals x, which is given, minus v t. We just solve for v, correct? And then we can say square root 1 minus v over c and squared, right? So this is given, and v we just solve for. We have the scenarios for both 1 and 2 for both those, we have the x1 and t1 and the x2 and t2 given to us in the question. So now essentially all we need to do is solve for our x1 prime, which will be equal to, I'm going to plug in the values they gave us, 40 minus 2.23 times 10 to the 8, and then 10 to the minus 9. So, yeah, it's 10 nanoseconds. And then divided by the square root. Oh, actually, I already solved this bottom part for you, but it's just going to be, you just plug into this equation, and what you'll end up coming out as is 0.667. This whole thing comes out to be 56.6 meters, right? So now we know x1 prime. So the next thing we're going to look for is x2 prime, which is going to be 60 minus same velocity 2. Wait, what? So in here times 10 to the 8. Don't forget that. 2.23 times 10 to the 8. And then our time here is 4.5 times 10 to the minus 8. And that whole thing is again going to be divided by that 0.667. And now I recall why we are using this instead of rewriting this every single time is, this is a long expression to plug into your calculator. Like this will take you a little bit, and it's hard sometimes on these simple calculators to do that whole thing at once. So if you solve it once, you can now plug it into every instance, which is going to be this problem, and for that matter, the next question. So we're not done here. Now we need to find the delta x prime, right? Where that equals x2 prime minus x1 prime, and that whole thing equals 18.3 meters, right? Oh, I forgot to say what this is equal to. So x2 prime equals 74.9 meters. Yes, 74.9 minus 56.6, and that will come out to be 18.3 meters. Okay, so that is part B, or part 2. What am I standing in front of? All right. So now in part 3, we're going to use an alternate expression here, and that's going to be for the times, right? Because we say here, oh yeah, so we just want to find the T2 prime minus T1 prime, which will equal the delta T prime, right? So the time between two flashes according to Bob. So that's actually, again, within our equation list here, where the Lorentz transformation equals that one that solves for x primes we just used, and the one that's going to solve for t prime, which is the equation we're going to now use. So what's our overall expression here? We're going to say, so yeah, we're looking for delta t prime. I'm sorry. Yeah, we are looking for delta t prime. The first thing we need to do is find t1 prime and t2 prime, but t prime itself equals t minus v over c squared times x, and then square root of 1 minus v over c, and then squared. And then again, remember, this is the same thing that we just used before, so hence further the reason why you should just solve for it once and keep using it. And we can see that t1 prime equals the time, so 10 to the minus 9 minus 0.745 c over c squared times that position, 40, divided by 0.667. Also, on my answer key, I wrote 10 to the minus 8 instead of 10 to the minus 9. So if my answers are, or if it looks different than the key, just keep that in mind. And that itself comes out to be minus 1.34 times 10 to the minus 7 seconds. And yeah, you do see a negative there, but don't be worried about that, because like per this problem, like there's going to be differences in the time that it's witnessed. So this kind of like allows us to frame the time as like before or after, essentially. And then the same thing here, we're going to accept it's going to be 4.5 times 10 to the minus 8 seconds, minus 0.745 c over c squared. So you guys can just cancel that out. And then times 60. And that whole thing again divided by 0.667. Okay, and then t prime, t2 prime equals minus 1.55 times 10 to the minus 7 seconds there. So now we need to find the change between these. So we're just going to subtract. I'm going to say delta t is going to be equal to that minus 1.55 times 10 to the minus 7. And then it's going to be minus a minus. So I'm going to add. So plus, and then, sorry, I ran out of space. 1.34 times 10 to the minus 7. And that whole expression should, I'm not going to write it, but it will come out to be negative 0.21 times 10 to the minus 7. All right, that's number 2. Let's check out number 3. Let me just erase. All right. So number 3 here, we have a fish that lives exactly 10 years. When it's born, it goes on a spaceship and blasts off at 0.8 times the speed of light from Earth, and as observed on, as measured by an observer on Earth. How old is the fish when it dies? Oh, I'm sorry. Geez. How far from Earth, as measured by an observer on Earth, is the fish when it dies? So we're looking for a distance here. So let's establish some of our variables. We have the proper time is 10 years, delta T naught equals 10 years, and we know V equals 0.8 C. So the first thing I'm going to do, and I'm going to have to solve this in 2 parts because we're asked for like a distance from Earth, is I need to first find the time. So I need to find delta T, that time dilation value. And using that time dilation value, I can solve for the distance per the property of, distance equals the velocity by times time, right? Where time in this case is going to be that delta T. And I'll write more about that later. Okay, so we know we're going to be using time dilation. I'm going to call this like essentially it's like part 1. So delta T equals delta T naught divided by the square root of 1 minus V over C squared. Okay, and we know it's going to be equal to 10 years. All right, 10 years. The square root of 1 minus 0.8 C divided by C squared. Cancel those guys out. And this whole thing will come out to be 16.7 years. And the reason why I solve for this first is now I can plug into the expression right here, which is, I'm going to purposely write it wrong first, and then I'm going to correct it, and then you guys will just remember this correction, you'll do it initially correct. So V equals, D equals V times delta T, right? So what is V equal to? We know it's equal to 0.8 times 3 times 10 to the 8 meters per second, right? Speed of light. And then I'm just going to plug in delta T, but that is an equal distance, right? So I'm plugging in 16.7 years. I can't cancel out years with seconds. So before I even do that, I need to convert my years into seconds, right? So that's just going to be like a long cancellation of units. So I'm going to say, so 365 day in 1 year. So now I can cancel that out. 24 hour in 1 day. So I can now cancel out my day. 60 minutes in 1 hour. Cancel out hours. And then 60 seconds in 1 minute. So I can cancel out minutes. You're going to now multiply the 16.7 times 365 times 24 times 60 times 60. And you're going to get a huge number. It's going to be equal to 50. Oh my gosh. 525 70 51 20 seconds. And I'm just going to call this alpha seconds. I don't want to rewrite that. And then you're just going to multiply this guy by alpha in the unit seconds. And now my seconds cancel out. So now my only units left here are meters. So essentially I have a distance now. So my distance here is going to be 1.262 times 10 to the 17 meters. And now we can just go back and kind of think about everything here is, as we previously discussed, our delta T is going to be greater than delta T naught. That's precisely the case. And, oh yeah, we didn't write anything about like contraction. Okay, so yeah, that's D. And for that matter, that's question number 3 done. All right, number 4 is kind of a quick one. It's just to kind of demonstrate that length contraction. So again, we have a particle traveling through Earth's atmosphere at 0.75 the speed of light. To an Earth-bound observer, it travels 2.5 kilometers. How far does it travel in the particle, in the moving frames frame of reference, right? So we have a stationary frame, which is 2.5, and we have L, which is the expected, like, is the distance by the moving frame, right? And we know that L is going to have a length contraction. So just right off the bat, we know L is going to come off, is going to be less than 2.5 kilometers, or at least that's what our intuition should be tipping us off. So you guessed it, we're going to use our length contraction equation here. So raise, it's going to be a quick one. So I'm going to say L, and I'm just going to plug in our L naught, so 2.5 square root, and then we're going to say 1 minus, what's the velocity? 0.75 c, and then c squared. Is that right? I messed up here. So I'm going to pop that squared out. Oh yeah, and these c's will cancel out, and L comes out to be 1.65 kilometers. All right. So yeah, double to make sure that's correct on when you're working through the key. Actually, I'll just cross it off right now. So that's going to bring us to number 5, and this one's kind of the big tuna of this worksheet, and very similar to question number 6 for that matter. I'm just going to pause real quick and grab some water. All right, so we're back now. So this is now number 5, similar to number 6 of the homework. We have a free neutron decays into a proton, electron, and neutrino. We're given like their symbols there. The mass of a proton is MP, the mass of a neutron is Mn, and the mass of an electron is Me, and the neutrino has no mass. Also, the neutrino moves at the speed of light. If the neutrino is at rest when it decays, how much energy is released when it decays, right? So essentially, we're going to say Ke is going to be equal to some change in the starting masses and then minus the products, right? So it's going to be delta M. I guess I should just write it. We're going to say Ke equals to delta M, so the mass starting minus products, and then C squared. So what's our starting here? We have the Mn, right? Because we have a neutron, and then it's going to be minus. What are the products? We're going to have the mass of the proton plus the mass of the electron, and I'm not going to even write the mass of the neutrino because we know that that equals 0. So that whole expression, C squared, that is part A. All right. So we have an equation there set up. And next, kind of part B, this is where there's just like a lot of algebra involved, and that's kind of why it's so tricky. We want to find, so now we want to assume that the electron is at rest after the collision, wherein the energy released is shared by the proton and the neutrino. Assume or determine the momentum of the proton and the neutrino after the decay. So they're going to have, first of all, they're going to have the same P, and we know two things are at rest at this point, that being the neutron and the electron. So we can kind of write like a starting guiding equation as E, N equals E of the proton plus E of the electron, and then plus E of the neutrino. And then now through if we express it through the relationship of energy and mass, where mc squared, and then per the fact that these guys are going to have momentum, we're going to see that there's going to need to be a total energy equation relative to those who are not at rest. So I'm going to denote the ones that are at rest by writing a little r in parentheses underneath it, right? They tell us that the neutron's at rest in part A, and now we know the electron's also at rest. So that means the momentum, as they tell us in the question, is going to be shared between the proton and the neutrino. So essentially, if we expand this equation, we're going to say mnc squared equals, and then now we need to recognize the total energy. So I'm going to say pc squared plus mp squared c to the fourth, close that off, square root, plus, mass of electron, c squared, also at rest, and then plus the square root of pc squared, plus, I'm just going to write it here, but then zero it out, me squared c to the fourth, mass, that's neutrino. So mass of the neutrino was equal to 0, so that means this whole part becomes 0, right? So we can I'm just going to erase it now, save room. So that whole thing equals 0. And also, we know that we can just get rid of this squared and square root terms here. The next thing I want to do is I want to get my subatomic particles, which are at rest on the same side, to kind of like factor out a c squared. And I also want to get this pc on the same side so I can get rid of the square root, right? So I want to get rid of the square root because I just want to be able to easily access my momentum values here. So I'm going to kind of combine the steps here. So I'm going to say mn minus me c squared minus p c, and then this whole thing is going to be squared to get rid of the square root. So that's going to be equal to pc squared plus mp squared c to the fourth. All right. Just make sure I'm not missing anything. So yeah, what I did, I brought this to the opposite side, factored out a c squared, then subtracted minus pc, and then I squared both sides to get rid of that square root. All right. So the next thing I want to do is actually square this entire term. So that's going to kind of be like algebraically brutal to do, but luckily I did it already. So we're going to, from this, we're going to have n. You see me if I'm writing all the way. I'm going to have mn minus, make sure I don't lose my spot here, minus me squared c to the fourth minus now 2, n minus me c to the third p, and then plus pc squared equals pc squared plus mp squared c to the fourth. All right, at this point, we can now cancel out these pc squared terms. And what we're left with is this, right? So the next thing I want to do is get these c to the fourth powers on the same side and get that cubed c to the opposite side. So I'm going to say mn minus me squared c to the fourth, and then going to be minus mp squared c to the fourth, and that equals 2mn minus me c cubed p. I'm going to get rid of that cube to get rid of these to the fourth powers. At this point, I can now factor out a c, and then I'm going to, all right, so we are right at the end. I'm going to factor out a c from both of these terms, and then I'm going to divide by 2 times mn minus me, so I have such that p is isolated on one side. So what is that going to look like? I'm going to say p is going to be equal to, so c times mn minus me, close parentheses there, that whole thing is squared, minus mp squared divided by 2 parentheses mn minus m. All right, so now we have what P is equal to. Obviously, I solved this no number. I'll leave the fun task of plugging in every single one of these masses to you guys. All right, and then that's going to bring us to part C of this question, which is we're going to be determining the kinetic energy of a proton. So the important thing about determining the kinetic energy of the proton is what was that equation? I'm sorry, again, that's not on the first page, but it's going to be the kinetic energy equals the total energy minus the rest mass energy. And that's going to be like relativistic kinetic energy, essentially. And what's the rest mass energy? That's just the mass c squared. And total energy can be expressed one of two ways. So again, now I'm referencing the formula table on page 1. We have total energy. We have two equations. We have one that uses velocity and then one that uses momentum as the present unknowns in this question. We just solved for momentum. We do not know velocity. So that means we're going to proceed with the, the energy total, which equals the momentum, right? So let's write this guy out. Actually, I think I'm just going to. I really can't even see. If you guys can see what I mean. All right. So now this is going to be part C here. We're going to say the kinetic energy is relativistic, Ke. Of course, I wrote it too high. So Ke equals, like I said, energy total. And then that minus that rest mass energy. In this case, that's the mass of a proton, c squared. And which energy total equation we're going to use? Like I said, the momentum one. So P c squared plus m p c squared, this whole thing squared, square root that, and then minus, sorry, I'm running out of space, m p c squared. So yeah, the energy total minus the rest mass energy, which is mpc squared. Yeah, so you guys, if you're actually gonna like do the question by plugging in the values like on the homework, yeah, so just gonna plug in what we saw for in part 2 into this part 3, and then you'll be able to get your kinetic energy. All right, I think that concludes our worksheet. Which review homework questions were reviewed was number 8, and obviously, I guess, number 6 for that matter. Thanks for watching.